Okay, we're going to continue with the next portion of this section, atoms, molecules, and the mole. What we want to take a look at now is atoms, molecules, and the mole. So the goals here to understand the mole concept and molar mass and its application. Use the molar mass of an element and Avogadro's number in calculations. Calculate the molar mass of a compound from its formula and a table of atomic weights. Calculate the amount, number of moles of a compound or an element represented by a given mass and vice versa. And use Avogadro's number to calculate the number of atoms or ions in a compound. So let's take a look at what we've got here. So a mole. A mole is the SI unit for measuring the amount of a substance. And by amount, we mean how many. Are there one? Are there two? Are there three? It just so happens that when we talk about atoms and molecules in a sample, it's not is there one or is there two or is there three? It's like, are there billions and billions and billions and billions, or billions and billions and billions and billions and billions? Okay, so it's a really large number. So what we have to do is we invented an amount that's going to be very useful for us to talk about that number. Just like with eggs or donuts, you don't talk about, yeah, you know what, I went to the store and I bought a donut. You say how many dozen donuts you bought or how many dozen cookies you made. In chemistry, our dozen is a mole. So just like the dozen means 12, it could be 12 of anything. 12 donuts. Well, I keep talking about food. 12 donuts, 12 cookies, 12 cars, 12 bicycles. You can have a mole of things, a mole of donuts, a mole of cars, a mole of popcorn, kernels that is. So a mole is just like a dozen, but it's a really big number. So the concept is so that the amount of an electron's atomic weight would be the same as the amount of the gram mass of a mole of atoms. So what does that mean? Well, here we have this nice periodic table with these atomic numbers at the top, the symbol in the middle, and the atomic weight at the bottom. So this is how much one average atom of hydrogen weighs. One atom is 1.008 AMUs. Now remember, the AMU is a certain amount of mass by gram, but we use the relative mass. It's kind of convenient, okay? Well, if we take a look at a hydrogen atom and we ask ourselves the question, how many atoms are in 1.008 grams, we could figure that out. And it's a really large number. Likewise, if we look at another element, so this element here is carbon, we could ask the question, how many carbon atoms are in 12.01 grams of carbon? So let's compare these two numbers. 1.008 AMU of hydrogen, that's one hydrogen atom. 12.01 AMU for one carbon atom. So we know that a carbon atom is 12 times more massive than a hydrogen atom because their relative masses are 12 times different, right? 12 over 1 is 12. Okay. So imagine, if you will, we had a gram of this, there would be a certain number of hydrogen atoms in there. Now imagine if we had 12 grams of carbon, 12 times the mass of 1 gram, how many carbon atoms would be in there? And the answer is, well, whatever that number is for hydrogen in 1 gram, there'd be the same number of carbon in 12 grams. And how can that be? Well, the answer is because carbon atoms are bigger. So if we had a mole of hydrogen atoms that weighed 1 gram, then a mole of carbon atoms, each weighing 12 AMUs, should weigh 12 grams. So what is that number? Well, we can actually calculate it. I'm going to get a piece of paper and calculate it for you. So this is an impromptu calculation. What I want to know is I want to know how many atoms are in 12 grams of carbon-12. So we have 12 grams of carbon-12, and I want to know how many atoms? Well, what I'm going to do is I'm going to take my 12 grams and I'm going to convert that into AMUs, and then I'm going to convert that into atoms. So here's what I need to know. I need to know that 1.661 times 10 to the minus 24 grams is equal to 1 AMU. That's good to 4 Zig Figs. It's not exact. And I also need to know that for a carbon 12 atom, it turns out that 12.00 AMU is equal to 1 carbon 12 atom. So remember, this is another way to write carbon 12. I don't have to put the 12 as a superscript. I can put it down here like this. So here we go. Let's take a look at our 12 point. We're going to say 12 exactly, 12 grams of carbon 12. And I'm going to multiply by 1.661 times 10 to the minus 24 grams of carbon 12 per 1 AMU of carbon 12. Okay, so I put this on the bottom so that those would cancel. Now I'm going to put down that there are, let's see, I want to get rid of the AMUs, so I'm going to put 12.00 AMU of carbon 12 per 1 carbon 12 atom. So again, I'm using my units to decide what goes on the top and what goes on the bottom. So here's the calculation. Now remember, this is exact, we're going to say. This has 4 Zig Figs, this has 4 Zig Figs. So we're going to end up with 4 significant figures at the end of this. Now, we can all see that 12 divided by 12 is 1. So basically, we have to take 1.661 times 10 to the minus 4 and divide it into 1. So when I do that, 1 divided by 1.661 second EE negative 24 is equal to, and we get 6.020 times 10 to the 23 carbon 12 atoms. Now that's really close to the number we expect it to be. So this is 1 mole of carbon 12. All right. So the answer to our question here is how many atoms? This many, and that's 1 mole of atoms. We could do the same thing for hydrogen. So if we take a look at another question, imagine we have 1.008 grams of hydrogen. How many hydrogen atoms? And here we're not looking at a specific isotope, we're just looking at general hydrogen atoms. We would make the same type of conversion. So we'd start off with 1.008 grams of hydrogen times 1 AMU, oops, excuse me, this is right, 1 AMU of hydrogen per 1.661 times 10 to the minus 24 grams of hydrogen. You might be wondering, how can I use this conversion down here for hydrogen and use it up here for carbon? Is that okay? Well, would we say that 16 ounces of steak is 1 pound of steak? You bet your bippy. Would we say 16 ounces of salmon is 1 pound of salmon? You bet your bippy. So we can use ounces and pounds for salmon or for steak? Yeah, you can even use it for vegetables. Okay, so let's take a look here. Now we're going to multiply by, here, instead of 1 carbon atom as being 12, we're going to say 1 hydrogen atom is 1.008 AMU. We get that from the periodic table. Now, it doesn't take a whole lot of effort to see that this is going to end up with the same result as above because, again, we have this divided by this is 1. So in reality, we have 1 divided by 1.661. So we get 6.020 times 10 to the 23 hydrogen atoms. Okay, so this number again is the number you find at the bottom of the symbol. And so here we can quickly realize that, you know what, we can look at that number there, think about it as being grams, and we know we have a mole of those atoms. Okay, so that's the concept of the molar mass. So back to the mole. If we look at this bottom number, not only is it the atomic weight, it's the molar mass. In words, the molar mass is the gram mass of 1 mole of a substance. And you want to memorize this number, that a mole is 6.022 times 10 to the 23rd. It's something you want to memorize, not have to look up. And there's a name for the mole, a nickname. It's called Avogadro's number, named after a famous scientist. There's even a symbol for Avogadro's number, N for number and A for Avogadro. Okay, so here we've already talked about this. How is the mole defined? It's the number of carbon atoms in exactly 12 grams of carbon-12. This is the amount of a mole, but it's not the concept. The concept is we want to be able to look at that bottom number and know how many particles there are in that many grams. So that number now means 2 things. It's the atomic weight, the weight or relative mass of one of these atoms, 24.31 AMU, or the gram mass of a mole of these atoms. And a mole is 6.022 times 10 to the 23rd. So these numbers look the same, but these amounts are vastly different. Remember, an AMU is very, very tiny, and 24.31 grams is massive compared to that. Okay, so memorize that number. Mass, moles, and atoms. So this is a question here from our book. Consider 2 elements in the same vertical column of the periodic table, lead and tin. What mass of lead in grams is equivalent to 2.50 moles of lead? So we're going to take our 2.50 mole of lead and we're going to turn that into grams. Now, can we do that directly? And the answer is absolutely, as long as we know about molar mass. So here's our book. Here's the periodic table. Let's find lead. And it looks like lead is right there, 207.2. So that means from our periodic table, lead 207.2, and the number on top is 82. This means that 1 mole of lead is 207.2 grams of lead. So that's what we're going to use to convert. So we're going to have 2.50 mole of lead times, now which side do I put in the bottom? That's right, 1 mole of lead. Why do I put the mole of lead in the bottom? So that these cancel. And the 207.2 grams of lead goes in the top. So here we can kind of estimate the answer, right? Because 2 times 207 is 414. And half of 207 is like 103. So 103 plus 414 puts us at about 517. So let's turn on a calculator and find out if we get around 517. 2.5 times 207.2, and we get 518 grams of lead. And there's our answer for A. And this is all the work you need to show to calculate the grams of lead in 2.50 moles. So let's take a look at B. So for B, what amount of tin in moles is represented by 36.6 grams of tin? So if we look at tin, which has the symbol SN, and I bring my periodic table over here, we see that we have 118.710 and 50. 118.710 and 50. Okay, so we're going to write 36.6 grams of tin times, and here, this is a little bit different. Instead of calculating the grams, we're calculating the moles, okay? Because it says what amount in moles. So here, I'm going to take my 1 mole of tin is equal to 118.710 grams of tin. And I'm going to put the 118.710 grams of tin in the denominator because I want the grams to cancel. Therefore, 1 mole of tin goes into the numerator. So this one is a little harder to estimate, but I think we can still do it. Can we see that 36 might go into 118 about 3 times? So this is roughly 1/3. So we expect the answer to be around 0.3, if you will. All right, so let's find out if that's the case. 36.6 divided by 118.710, and we get 0.308 mole of tin. And this is the amount of work I would expect to see for what you calculate for how many moles. Now, why does it only have 3 significant figures when this has 6 significant figures? And the answer is, well, because that only has 3 here. Well, what about the 1 here? Well, the idea here is that for these types of conversions where you have a 1 on part of the conversion, 1 on one side, that's exactly 1, okay? All right, now what about the second part? How many atoms of tin are in the sample? Now we can start with this answer here, or we can start here. So let's pretend that in this particular question, we weren't asked this to begin with. We were just asked how many atoms. Well, this is how you might do it. 36.6 grams of tin times 1 mole of tin per 118.710 grams of tin, and then times 1 mole of tin on the bottom. And what's the numerical amount of a mole? That's right, 6.022 times 10 to the 23rd. And we're going to put atoms of tin because that's what we're talking about. Now, to estimate this, we would have 0.3 times 6, or 1/3 of 6. Let's see, 1/3 of 6 is about 2, right? So our answer should be around 2 times 10 to the 23rd. So let's find out what we get. So I've already got the beginning part of the number. I'm going to put times 6.022 second EE 23. And we get 1.86 times 10 to the 23rd tin atoms. And that's the kind of work I would expect to see for how many atoms of tin are in the sample. Okay, let's move along here. Next, we have for molecules, compounds, and molar mass, we have formulas of compounds. Because we're going to be looking at some more ways of using the mole and molar mass, so to speak. So the formula, it tells you the ratio of atoms. So when we see CO2, that means 1 carbon atom to 2 oxygen atoms. So I'm going to put a little dot there so that we can see that the O is not a 0. It also tells you the ratio of moles of atoms. So this says that for CO2, there's 1 mole of carbon to 2 moles of oxygen. If this were a cooking class, we would probably say 1 cup of carbon to 2 cups of oxygen, or something like that. So the formula are equivalencies. We can actually say that if you had 1 molecule of CO2, that would be 1 carbon atom and 2 oxygen atoms. Or if you had 1 mole of CO2, it's 1 mole of carbon atoms and 2 mole of oxygen atoms. So when you have an equivalency like that, it's a conversion factor. a potential conversion factor. So let's look at molar mass and Avogadro's number in some more calculations. So here, let's calculate the moles of ethanol in 22 grams, 22 grams of ethanol. Here is the formula. Okay, now to calculate this, we need the molar mass of ethanol. And let's see, actually, I want to go, we have a slide too early. So to back it up to this slide, don't you find it interesting that I call pieces of paper slides? Because this is almost like a PowerPoint show, only with real paper. Anyway, that's not necessarily a good thing, is it? Oh well. So let's look at molar mass of a substance before we go into using these for calculations. So this is the mass of 1 mole of a substance. So this is the mass of 6.022 times 10 to the 23rd of something. To get the molar mass of a substance, you sum the molar mass of each atom in that substance. So for instance, the molar mass of bromine is going to be the molar mass of 1 bromine plus the molar mass of another bromine, where this is the molecular bromine, if you will, where the 2 atoms are held together by a covalent bond, and these are atomic bromines. So atomic bromine, molecular bromine. So this is the same as saying 2 times the molar mass of 1 bromine. So the molar mass of 1 bromine is 79.90 grams. I got that from the periodic table. So here is the molar mass of Br2 molecular bromine. It's 159.8 grams. What's the molar mass of C2H6O? Well, it's 2 moles of carbon plus 6 moles of hydrogen plus 1 mole of oxygen, which is 2 times 12.01 grams, because each mole of carbon is 12.01 grams, 6 times 1.008 grams, because each mole of hydrogen is 1.008 grams, and 1 times 16.00, because each mole of oxygen is 16.00 grams. When we add these all up together and round appropriately, we get 46.07 grams. So 1 mole of C2H6O is 46.07 grams of C2H6O. And now we're ready for this slide where we're going to use the molar mass and Avogadro's number in calculations. So we're going to calculate the moles of ethanol in C2H6O in 22 grams of ethanol. Now we just did the molar mass of this compound here, and it was 46.07 grams. So again, we can convert from grams to moles directly using the molar mass of ethanol, and here's the way it looks. 22.2 grams of ethanol times 1 mole of ethanol per 46.07 grams of ethanol. And you can see that the grams of ethanol cancel, and we're left with mole of ethanol. And when we do the work, you can see that 22 divided by 46 is going to be close to half, and indeed our answer is close to half. Why 2 significant figures? And the answer is because the 22 has 2 significant figures, the 1 is infinite, and the 46.07 is 4. So when I have the multiplication rule for rounding, I'm going to round to 2 sig figs, the lowest number of significant figures in any of the beginning numbers. Calculate the moles of atoms in 22 grams of ethanol. So we've done this before. We're going to take our 22 grams, turn it into moles, and then turn it into moles of atoms. Okay. Now, we haven't done quite this, but this is a little bit different. But 22 grams of ethanol, this is the same conversion as above. And here, 9 mole of atoms per 1 mole of ethanol. How do I get 9 mole of atoms? Well, remember, if I have 1 mole of this, that means 2 mole of carbon, 6 mole of hydrogen plus the 2 for carbon is 8 plus 1 oxygen. That's 9 mole of atoms, okay? So I have 9 mole of atoms per 1 mole of ethanol. You might be wondering what happened to the rest of the spelling of ethanol? And the answer is this is a common abbreviation for ethanol, ET, uppercase O, uppercase H. Okay, so when we do this work, remember 22 divided by 46 is about half. Half of 9 should be about 4.5. And indeed our answer is about 4.5 mole of atoms. Okay, so that's a lot of atoms. Now, let's calculate the molecules of ethanol in 22 grams. So we keep adding to this here. So here we have our 22 grams times 1 mole per 47 grams. And instead here of saying mole of atoms per mole of ethanol, we're going to say that we have this many molecules of ethanol per 1 mole of ethanol. So we can actually, if we want, put in molecule here. Now, how do we know this is a molecule and not an ionic compound? And the answer is because all of the elements are nonmetals. So we can actually put in molecule here. All right, so divided by 46 is roughly half. Half of 6 is 3, so our answer should be around 3 times 10 to the 23rd, and indeed it is. And you know why it has 2 zig figs, because of the 22 over here. Calculate the number of atoms in 22 grams of ethanol. So we just keep adding to this. So we can see that we can start here, essentially, that many molecules, and we know that there are 9 atoms per 1 molecule. So we get 2.6 times 10 to the 24. I've shown you another way to do it down here, where instead of going from gram to molecules to atoms, we go from gram to moles of atoms to total number of atoms. So here, the first conversion is the same. We have 9 mole of atoms to 1 mole of ethanol. And then here, we say that there's that many atoms per 1 mole of atoms. And we get the same answer as above. So these are the types of calculations you want to familiarize yourself with. And you want to look in the book and see if there are problems that are like this and give them a try, for goodness sakes. The best way to prepare for the test is to be able to do a problem like this without having to go look for help. Because when you go look for help, like on a note card on your exam, you're losing time. And these tests are timed. Now, the reason they're timed is because you should know the material well. And if you don't know it well, you won't do as well on the exam. So you need to prepare. Okay. Next, we have molar mass in moles. Here's another problem from the book. You have 16.5 grams of oxalic acid. What amount is represented by 16.5 grams of oxalic acid? So you can see that for this part here, we want to take our 16.5 grams and turn that into moles. And there we go. So what kind of conversion do we need to go from grams to moles? We need molar mass. So that's one of the things we need to do for this particular problem is figure out the molar mass of oxalic acid. How many molecules of oxalic acid are in 16.5 grams of the acid? Well, we'll take our 16.5 grams, turn that into moles, and then we'll turn that into molecules. So these are different words, mind you. One is not the abbreviation of the other. Mole is an amount and molecule is a type of a particle. How many atoms of carbon are in oxalic acid? My suggestion is we do 16.5 grams to moles to molecules and then to carbon atoms. So let's calculate the molar mass. Molar mass of H2C2O4 is going to be equal to 2 mole of hydrogen plus 2 mole of carbon plus 4 mole of oxygen. So that's going to be equal to 2 times 1.008 grams of hydrogen plus 2 times 12.01 grams of carbon plus 4 times 16.00 grams of oxygen. So you'll notice I'm not putting grams of hydrogen here and grams of carbon and grams of oxygen because it doesn't matter where the grams come from. We just want the total. Now, if I want to estimate this, 4 times 16 is roughly 64. 64 plus 24 is 88. 88 plus 2 gives me 90. So I should get around 90 for my answer. 2 times 1.008 plus 2 times 12.01 plus 4 times 16.00. And we get, I'm going to change this to flow. We get 90.04 grams. Okay, so this means that 1 mole of oxalic acid is 90.04 grams. So I'm using OA as an abbreviation for oxalic acid because I don't want to write H2C2O4 again and again. Okay, so we're prepared to do A. For B, what do we need to know here? Well, for here, I'm going to call this 1. I'm going to call this 2. For 2, we need to know that there's 6.022 times 10 to the 23rd molecules is equal to 1 mole. And we can even put oxalic acid and oxalic acid here. And here, what do we need for this? For 3, we need to know that based on the formula, that we have 2 carbon atoms per 1 oxalic acid, right? 2 carbon atoms per 1 oxalic acid. So we have all the conversions we need for A, B, and C. Let's go about and do them. A, 16.5 grams of oxalic acid times 1 mole of oxalic acid per 90.04 grams of oxalic acid. And we have 16 divided by 90. 16 will go into 90 about 6 times, so this is 1/6.15-ish. All right, so let's find out. 16.5 divided by 90.04. Oops. I wrote 60.04, that wouldn't be good. 90.04. Now for estimating, if you're not good at estimating and kind of figuring out what the fraction is here, there's a lot of different ways to kind of make it faster for you. So one of the things you could do when you first begin estimating is you could look at these numbers and ask yourself, should my number be bigger than 1 or smaller than 1? Or should it be a lot bigger than 1 or a lot smaller than 1? Here, you can see that the number is going to be smaller than 1, but not as small as 1/10. Bigger than 1/10, smaller than 1. And so here we get 0.183 mole of oxalic acid. So that's definitely bigger than 1/10 and smaller than 1. For B, we have 16.5 grams of oxalic acid times 1 mole of oxalic acid per 90.04 grams of oxalic acid. And then we're going to convert it into molecules. So there's 6.022 times 10 to the 23rd molecules of oxalic acid per 1 mole of oxalic acid. So if I multiply 6 times 0.183, I'm going to get around 1. And times 10 to the 23rd. So times 6.022, second EE, 23, and we get 1.10 times 10 to the 23rd molecules of oxalic acid. Okay, now if we take a look here, I could potentially start with this number and get C. But what would be better is if I started with 1.10 and put a little arrow here, 3.5 times 10 to the 23 molecules of oxalic acid. Now the reason I'm doing that is because we're not supposed to round early. And if we started with this number, that would be rounding early. I have a little arrow pointing out that this is good to the 0. 3 zig figs because of the 3 zig figs here. And here, our last thing is that we have 2 carbon atoms per 1 molecule of oxalic acid. So here I could put the word molecule here. So here we can see that roughly the answer is going to be 2.2. But let's see what we get. 2.2 times 10 to the 23rd. Times 2. So Whoops. What did I do wrong here? Oh, I divided by 2. Do you see that? So I got to multiply by 2, get it back to the 1.1, and then multiply by 2. And here, remember how I said if we doubled that, we get 2.20? Well, look, we didn't round early, and we actually get 2.21 times 10 to the 23rd carbon atoms. And that's why you don't round early. Okay, so that's molar mass in moles. Next lecture, we're going to be looking at chemical analysis and determining compound formulas. We'll be doing some labs based on this also. We'll also be doing some labs based on mass spectrometry, which will be coming in the next lecture, or maybe the lecture after that. I'm not sure if this is going to be one more lecture or 2 more lectures. At any rate, thank you for listening. I hope you took some notes, and toodles.